Dear students, in this video, I am going to discuss numerical problems appeared in the year March 2017. Watch full video that helps you to score more in the upcoming examination. Let's have a look on the very first problem. 2-point charges QA equals to 3 microcoulomb, QB equals to minus 3 microcoulomb are located 20 centimeter apart in vacuum. What is the electric field at the midpoint O of the line AB joining the two charges? If a negative test charge of magnitude 1.5 into 10 raised to minus 9 coulomb is placed at this point, what is the force experienced by the test charge? Here we have 2-point charges, that is QA and QB, which are placed at a distance of 20 centimeter. The position of QA is A and this is B. So we need to find out the electric field at the midpoint O of the line AB. Let us consider this is the midpoint of the line AB, which is going to join the two charges. Here we need to find out the net electric field at the point O. So here we have QA equals to 3 microcoulomb and QB is equals to minus 3 microcoulomb. As we know that electric field due to isolated point charge is equals to 1 by 4 pi epsilon naught Q divided by R square. Q is the magnitude of the charge and R is the distance of point of concentration from the charge. That means the distance of point of concentration is here O, and then we have to measure the distance of O from A as well as B. Here O is the midpoint, so we can write AO is equals to BO, that is AO is equals to BO, that is equals to AB by 2. So we know that AB equals to 20 centimeter, so AB by 2 is 10 centimeter. This can be written as 10 to the power of minus 1 meter, because centi means 10 to the power of minus 2. 10 to the power of minus 2 into 10, 10 to the power of minus 1 meter. This is the distance of point of concentration from A as well as B. Here the electric field due to the charge QA can be considered as EA, which is acting towards O, because QA is positive charge, and electric field due to the charge QB can be considered as EB, which is acting towards B, because it is a negative charge. Okay, so because of the positive charge, the electric fields are moving away from the charge, and negative charge, the electric fields are terminated at the negative charge. So we can show the electric field towards the negative charge and electric field away from the positive charge. So now we can see that EA and EB both are acting in the same direction. So we need to find out the net electric field at the point O. The net electric field at the point O, that is E net electric field at the point O, can be written as EA plus EB, because the electric field due to the charge QA as well as electric field due to the charge QB both are acting in the same direction, so we can add them up. Here we know that EA can be written as 1 by 4 pi epsilon naught QA divided by EO square plus 1 by 4 pi epsilon naught QB divided by BO square. So as we know that here 1 by 4 pi epsilon naught as well as EO and BO can be taken outside. Here 1 by 4 pi epsilon, let me take out 1 by 4 pi epsilon naught, and then let me write here QA divided by AO square plus QB divided by BO square. On substituting the values, we can get, that is E net is equals to, E net, the net electric field at the point O can be written as 1 by 4 pi epsilon naught, value is 9 into 10 raised to 9, and QA is 3 microcoulomb, micro means 10 raised to minus 6, divided by AO square. AO means here AO equals to BO equals to 10 to the power minus 1. 10 to the power minus 1 square plus QB equals to 3 into 10 raised to minus 6. You are not supposed to take negative here. The negative sign indicates that the electric field lines are acting towards the B. So we need to consider only magnitude of the charge because the electric field is a vector quantity. So next here BO, that is BO square. BO equals to 10 raised to minus 1 whole square. So here we have 10 to the power of minus 1 whole square, 10 to the power of minus 1 whole square. It's same. So let me take them outside. We'll get 9 into 10 raised to 9 divided by 10 to the power of minus 1 whole square is nothing but 10 to the power of minus 2. So here we can take them outside. We'll get 3 into 10 raised to minus 6 plus 3 into 10 raised to minus 6. On simplifying, we get that is 9 into 10 raised to 11, because 10 to the power of minus 2, when it goes up, it will become 10 to the power of plus 2. So we will get 10 to the power of 11 into 3 plus 3, 6 into 10 raised to minus 6. So this is equals to 9 6 54 into 10 raised to 5 Newton per coulomb. This is what 54 into 10 raised to 5, or else we can write 5.4 into 10 to the power of 6 Newton per coulomb is the electric field at the point O. This is the electric field at the point O. Now we have one more question, that is we need to find out the force experienced by the test charge which is placed at O. We know that the force experienced by the test charge is force equals to net electric field at the point O into test charge. So the magnitude of the test charge is equals to 1.5 into 10 raised to minus 9. That is the net charge equals to 5.4 into 10 raised to 6 into the test charge value is 1.5 into 10 raised to minus 9. So when you simplify this, we'll get 5.4 into 1.5. This will become 8.1 into 10 raised to minus 3 Newton. This is the force experienced by the test charge which is placed at O. So let's have a look on the next question. That is, when two resistors are connected in series with a cell of EMF 2 volt and negligible internal resistance, a current of 2 by 5 ampere flows in the circuit. When the resistors are connected in parallel, the main current is 5 by 3 ampere. Calculate the resistances. See, whenever we connect two resistors, let me consider those resistors are R1 and R2. When we connect two resistors in series, that is the effective resistance will become R1 plus R2. At the time we will get an current of 2 by 5, that is IS. Let me say current in the series circuit, that is IS equals to 2 by 5 ampere. When it is connected to the source, V equals to 2 volt. And when the same resistors are connected in parallel, we get Rp is equals to R1 R2 divided by R1 plus R2. We will get IP is equals to 5 by 3 ampere. 5 by 3 ampere, and source is same, that is 2 volt. So we need to find out R1 and R2. As we know that from the Ohm's law, we can write the R is equals to, that is resistance, net resistance is equals to the voltage V by I. Let me write RS is equals to V divided by IS. So we'll get here V equals to 2 volt and IS equals to 2 divided by 5. Thereby we'll get 5 ohm is the RS value. That is nothing but R1 plus R2 is equals to 5. Let me consider this equation number 1. Now you look at this Rp, that is, we know that Rp is equals to V divided by Ip. From the Ohm's law we can write like this. So we know that Rp is equals to R1 R2 divided by R1 plus R2. This can be written as V equals to 2 divided by Ip equals to 5 by 3. 5 divided by 3. This is equals to 6 divided by 5. So now R1 R2 divided by R1 plus R2, as we know that 5 equals to R1 R2 divided by 5 equals to 6 divided by 5. So we will get R1 R2 equals to 6. So by using these two we can find out now R1 and R2. So as we all know that R1 minus R2 whole square can be written as R1 plus R2 whole square minus 4R1 R2. Now on substituting these values of the R1 plus R2 as well as R1 R2, we can get R1 minus R2 value, that is R1 minus R2 whole square is equals to R1 plus R2 value is 5, that is 5 square, minus 4 into, that is R1 R2, that is 6. So we will get here 5 square is 25, 25 minus 24, that is equals to 1, that is R1 minus R2 whole square equals to 1, that is R1 minus R2 equals to 1. This is equation number 2. So from 1 and 2, that is R1 plus R2 equals to 5 and R1 minus R2 equals to 1. Here we have R1 plus R2 is equals to 5 and R1 minus R2 equals to 1. So I am solving this, that is R2 get cancelled, so we will get 2R1 is equals to 6. So therefore R1 is equals to how much? 3. R1 is equals to 3 ohm. So this one should be substituted in any one of the equation, that is in this equation or in this equation. We will get R2, that is R1 plus R2 equals to 5. Here R1 is 3 ohm, 3 plus R2 equals to 5. So therefore R2 is equals to 5 minus 3, 2 ohm. This is R2. So R1 is, so therefore we can say R1 equals to 3 ohm and R2 is equals to 2 ohm. Okay. Let's go to the next question, that is a source of alternating EMF of 220 volt 50 Hertz is connected in series with a resistance of 200 ohm, an inductance 100 millihenry and a capacitance of 30 microfarad. Does the current lead or lag the voltage and by what angle? So first let me write the given data here first. The source of alternating EMF, that is V equals to 220 volt and frequency of the AC equals to 50 Hertz, and here we have resistance R is equals to 200 ohm and inductance L is equals to 100 and 100 milli, that is 10 to the power minus 3 Henry, that can be written as 10 power minus 1 Henry. And here we have capacitance, that is equals to 30 microfarad, that is 30 into 10 raised to minus 6 farad. So as we all know that if XL is greater than XC, that is if inductive reactance is greater than capacitive reactance, then V leads the current. V leads the current. If XC is greater than XL, then I leads the voltage. Now let's check whether the current lead or lag the voltage, okay, by checking XC and XL. As we all know that XL is equals to 2 pi FL, that is inductive reactance is equals to 2 pi FL. On substituting the values, 2 into 3.142 into F is 50 and L is equals to how much here? 10 power minus 1. 50 into 10 power minus 1, 5. 5 into 2, 10. 10 into 3.142, that is equals to 31.42 ohm. This much we have, that is XL. Now let's find out XC. We know that the capacitive reactance is equals to 1 divided by 2 pi Fc. So this is equals to, on substituting, we get 2 into 3.142 into F is 50 and into the capacitance, that is 30 into 10 raised to minus 6. So on simplifying we get, that is 2 into 3.142 into 50. So if you simplify, we'll get into 30, we'll get 9426 into 10 raised to minus 6. Now we could write this one as 1 divided by 9.426 into 10 raised to minus 3. Okay. Now this 10 raised to minus 3, if it comes to the numerator, then it will become 1000 divided by 9.426. So then the value of XC becomes 106.08 ohm. So here we got the XL value as well as XC value. So XL value is, that is XL equals to 31.42 ohm and XC value is 106.08. So therefore here XC is greater than XL. So we could write that the current leads the voltage. Now we need to find out the angle. So we know that to find out the angle, we know that by the phasor diagram, psi equals to, that is phase angle is equals to tan inverse of, here XC is greater, so we can take XC minus XL divided by R. And substituting the values, we get now tan inverse of XC value is 31.4, sorry, XC value is 106.08 minus 31.42 divided by the resistance is 200 here. The resistance is 200. So let me substitute here. So on simplifying, we get, that is tan inverse of 0.3733. Now look at the natural tangents. We get, when you look at the natural tangents to find out the value of this angle, you can see now 0.3733. Here you can see 3733. Here in 37 we have here 3733. Here you can get 3733. Here you can see 3739. The very nearest value here we have 3739, and we can see the degree here, that is 20. That is 20. We have 20 degree and 30 minute is nearest value. So we can get now 20 degree 30 minute. So 20 degree 30 minute we have. So we can write now here 20 degree 30 minute. That is 20 degree 30 minute. This is the phase angle. Okay. Now we got the phase angle as well as, that is phase angle is 20 degree 30 minutes. Okay. So let's have a look on the next problem. That is, light of wavelength 6000 angstrom is used to obtain interference fringes of width 6 mm in a Young's double slit experiment. Calculate the wavelength of the light required to obtain fringe width 4 mm when the distance between the screen and the slit is reduced to half of its initial value. So first let me consider the given data here. So here we have a wavelength, that is, let me consider lambda 1 equals to 6000. Why I am considering lambda 1 here? Because we need to find out lambda 2. So we are going to find out the wavelength of the light required to obtain the fringe width. So we are going to find out lambda. So let me consider given wavelength as lambda 1, and the wavelength to be found can be considered as lambda 2. Now here the fringe width, when we use 6000 angstrom, is beta 1. Let me write beta 1 equals to 6 millimeter, that is 6 into 10 raised to minus 5 meter. This is equals to 6000 into 10 raised to minus 10 meter. Now calculate the wavelength of the light required. We need to calculate the wavelength of the light required to get the fringe width, that is beta 2, 4 millimeter. When the distance between the screen and the slit is reduced to half. Let me consider the initial distance is d1, that is equals to d, and now we are going to decrease that distance, that is half of its initial value, that is equals to d2 equals to d by 2. So now we need to find out the wavelength of the light used to get the fringe width, that is 4 into 10 to the power minus 3 millimeter, when the distance between the screen and the slit is reduced to half of its initial value. So as we know that the fringe width is equals to beta equals to lambda d divided by d. Here we have two situations. Let me consider beta 1 as well as lambda 1 and d1, and the distance between the two slits remains same. The small d is the distance between the two slits, capital D is the distance between the screen and the slits. So now beta 2 can be written as in this. Beta 2 can be written as lambda 2 d2 divided by d. Let me take ratio between beta 1 and beta 2. Then we will get beta 1 divided by beta 2 can be written as lambda 1 d1 divided by d divided by lambda 2 into d2. We could write like this. dt get cancels. We get lambda 1 by lambda 2, that is d1 equals to d, and d2 equals to, we know that d by 2. Let me write d by 2. So here dt get cancels, we'll get 2 lambda 1 divided by lambda 2. So beta 1 divided by beta 2 equals to 2 lambda 1 divided by lambda 2. Make lambda 2 as a subject formula because we need to find out lambda 2. So we will get lambda 2 equals to, now lambda 2 equals to beta 2 2 lambda 1 divided by beta 1. This is the lambda 2. So when you substitute the values, that is beta 2 equals to 4 times 10 raised to minus 3 into 2 into lambda 1 is 6000 angstrom. 6000 angstrom divided by beta 1. Beta 1 equals to 6 into 10 raised to minus 3. So this is 10 raised to minus 3, 10 raised to minus 3, it cancels. 2 1 ja, 2 3 ja, 3 1 ja, 3 ja, so 4 2 ja, 8 will get, that is 8000 into 10 raised to minus 10, that is lambda 2. So lambda 2 equals to how much? 8000 angstrom. This is the wavelength of the light required to obtain the fringe width of 4 into 10 to the power minus 3 meter when the screen and the slit is reduced to half of its initial value. Okay, let's go to the next question, that is the first member of the Balmer series of hydrogen atom has wavelength 6563 angstrom. Calculate the wavelength and frequency of the second member of the same series. The speed of the light is 3 into 10 raised to 8 meter per second. Here we have the first member of the Balmer series of hydrogen has wavelength. Let it be lambda 1. That is lambda 1 is equals to 6563 angstrom. That is 10 raised to minus 10 meter. We need to find out the wavelength and frequency of the same series. That is lambda 2 we need to find out, as well as frequency of the same series, that is Balmer series. Let us see. Now we know that the Balmer formula, that is 1 by lambda equals to r of 1 divided by n1 square minus 1 divided by n2 square. As we know that for Balmer series n1 should be equals to 2, and for first member of the Balmer series, N2 should be equals to 3. So on substituting, we get 1 by lambda 1 is equals to R of 1 by 2 square minus 1 by 3 square. So simplifying, we get it is R of 1 by 4 minus 1 by 9. This can be written as, that is 1 by lambda 1 is equals to R of, so 36 to here 9 minus 4. We get R of 5 divided by 36. So you make lambda 1 as a subject formula. So we get lambda 1 is equals to 36 divided by 5R. That would be equation number 1. Now let me take for the second member of the Balmer series. For second member of the Balmer series, N2 should be equals to 4. So we get 1 by lambda 2 equals to 1 by R of 1 by 2 square. For Balmer series is same, minus 1 divided by 4 square. This can be written as R of 1 by 4 minus 1 by 16. This can be written as now, that is R of 16 into 4 minus 1. This is equals to 3R divided by 16. So make lambda 2 as subject formula. So lambda 2 becomes 16 divided by 3R. This is equation number 2. Divide now lambda 2 by lambda 1. On dividing lambda 2 lambda 1, we get lambda 2 by lambda 1 is equals to 16 by 3R into 5R by 36. R and R get cancels. We get 16 by 3 into 5 by 36. This is equals to, that is lambda 2 by lambda 1 is equals to 16 into 5, 80 divided by 36 into 3, that is 108. Now lambda 2 becomes, that is lambda 2. So let me write once again, that is lambda 2 by lambda 1 is equals to, here we have 80 divided by 108. It is 80 divided by 108 we got. Now if lambda 2 comes to the right side, then it will become lambda 1 here. So now 80 divided by 108 into lambda 1. So here lambda 1 value is 6563 angstrom. It is 6563 into 10 raised to minus 10 meter. So we get lambda 2 is equals to, on simplifying, we get lambda 2 equals to 4861 angstrom. So that is what lambda 2. So lambda 2 equals, so therefore we can write lambda 2 equals to 4861 angstrom. This is one thing. The next question is, we need to find out frequency. The next one is, we need to find out here frequency. So as we know that V equals to F lambda, as we know that the C, that is velocity of light, equals to frequency and lambda. So here frequency can be written as C divided by lambda. So now the second member, or the frequency of the second member we need to find out. So we can write here lambda 2. That is frequency of the second member of the Balmer series is 3 into 10 raised to 8 divided by lambda 2 is 4861 into 10 raised to minus 10 angstrom. This is equals to, on simplifying, we get 6.171 into 10 raised to 14 hertz. This is the frequency of the second member of the Balmer series, and this one is the wavelength of the second member of the Balmer series. Okay. Thank you. Thanks for watching.